Let's take a look at the power-reducing identities and the half-angle identities. The double-angle identity for cosine can be written in a few different ways, and we can use these alternate forms to express cosine squared and sine squared in terms of cosine of 2x. And so the idea of a power-reducing identity is a way to reduce the square of a trigonometric function, a higher power, into a lower power. Of course, the angle becomes a little bit more complicated because we go from x to 2x, but sometimes that can be a real advantage in terms of working with a trigonometric expression. So let's take the first example. If I have cosine of 2x, if I set that equal to 2 cosine squared x minus 1, or if I think of that identity, that pairing of cosine 2x, it equals 2 cosine squared x minus 1. I can solve for cosine squared by adding 1 to the other side and dividing by 2. And so I get cosine squared of x is equal to 1 plus cosine of 2x, adding that 1 to the other side, and then dividing everything by 2. In a similar way, if we think of cosine squared x as equal to 1 minus 2 sine squared x, if we take that alternate form for the double angle identity, solving for sine squared, and we end up with sine squared of x equals 1 minus cosine of 2x divided by 2, because the cosine of 2x would become negative and the sine squared would become positive on the other side. So these are called the power-reducing identities because they reduce the power of sine squared and cosine squared to just a linear expression in terms of cosine of 2x. We can also use these to think about half-angle identities because x is equal to 2x divided by 2. If I think of x as equaling theta over 2, then 2x equals theta. And so by doing a substitution, I can express cosine of theta over 2 in terms of cosine of theta. Because what's important to recognize here is not exactly the symbols that are used in these identities, but the relationships they describe. And x and 2x are related because 2x is always twice x. So theta and theta over 2 are related in the same way because theta is exactly twice as much as theta over 2. And in a similar way, we can come up with a half-angle identity for sine. Sine squared of theta over 2 is equal to 1 minus cosine of theta divided by 2. Taking the square root of both sides, we end up with the half-angle identities. Cosine of theta over 2 is equal to the square root of 1 plus cosine of theta divided by 2, and sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine of theta over 2. So these are the half-angle identities for cosine and sine. They're a little bit complicated by the fact that for any particular value of theta, the answer is either going to be positive or negative, and if we add one full rotation, it's going to change the sign from positive to negative. So let me demonstrate that situation with a quick example. Suppose we take theta equal to something that we know. Let's say we take theta equal to 120 degrees. So then what this relationship is saying, well, we know that cosine of 120 degrees is equal to 1/2. And what this is saying, so then the half-angle identity for cosine would give us cosine of 60 degrees, because 60 degrees is half of 120. Well, I know that the cosine of 60 degrees is going to be positive. So I'm going to take the positive square root, and I get 1 plus cosine of 120, where 60 and 120, they have that relationship where 60 is half the angle 120. And I know that the cosine of 120 is 1/2. So I have the square root of 1 plus 1/2 divided by 2. But that's the same as the square root of 1.5 divided by 2, which is the same as the square root of 3 over 4. And splitting the square root to both factors, that's the same as the square root of 3 over 2, which we know from earlier examples that that's cosine of 60. So with that example in mind, let's think about what would happen if I add one full rotation to 120 degrees. So what if we took theta to be 480 degrees, adding 360 degrees, adding a full rotation? Then theta over 2 is going to be half that, 240 degrees. Cosine of 480 is going to be the same as cosine of 120. It's going to be 1/2. But the angle 240 degrees turns out to be in the third quadrant, and so I know that the value for cosine there should be negative. So the issue is that when we add a full rotation to theta, it gives us exactly the same value as 120. So 480 degrees is the same as 120 for cosine. But when we take the half angle, then that's like adding 180 degrees. So that takes me to the opposite side of the circle and gives me the opposite value for cosine. So rather than getting positive square root of 3, we're going to get a negative square root of 3 over 2. And so we would want to think of this as cosine of 240 degrees. It's going to equal negative square root of 1 plus cosine of 480 over 2, which would work out to be negative square root of 3 over 2. And so the half angle identities do have that kind of added complication of plus or minus signs. Fortunately, that doesn't come up too much in the way that we use them, but it can sometimes be an issue. So let me end the video with a question. I encourage you to take a few minutes and try to use the half angle identity for sine to find an exact expression for sine of 67.5 degrees. And it will help to think of 67.5 degrees as 135 divided by 2. I hope you enjoyed the video. Thanks for watching.